All right, let's get started. All right, this gets us into chapter 7. This is kind of the biggest conceptual reaction piece, if that's a thing of the semester. The things we talk about in this reaction are in this chapter about these reactions are going to carry through to all the rest of everything else that we do. These reactions in some ways have the more simple mechanism than what we saw in the addition mechanisms, but the difficulty here is going to be often deciding what is going to happen or how to make something happen. So what we're talking about here is a set of two reactions, and we talk about them together because they happen with the same types of reagents. And the reagents that we're going to be mostly dealing with here are alkyl halides, that is, things where you have a bunch of carbon and hydrogen and then a halogen. So let's say we mix a molecule like this with this molecule, which is the conjugate base of ethanol, known as ethoxide. So ethanol loses a hydrogen, becomes ethoxide, which is an ionic compound. So it would be sodium ethoxide here, but the ethoxide part, this is going to be a really strong base. Right? Something that is highly negatively charged and really strongly attracts positively charged stuff. There are two reactions that can happen when these two are mixed. The first one looks like this. This highly negatively charged ethoxide sees this carbon over here, which is somewhat polar. This carbon-bromine bond is going to be somewhat polar, meaning this carbon is partially positive, this bromine is partially negative. So this is nucleophilic, goes to the partially positive electrophilic carbon. And since we can't have all that stuff attached at the same time, the bromine leaves in return. So now what we have is this thing connected to that ring, and the byproducts of sodium and bromide. And this is called a substitution reaction. Specifically, it's called an SN2 reaction, but we're going to get into that later, what that means. Substitution, I think you can see why it means that, or why it's called that. One thing has substituted for another and being attached to that carbon. Good so far? All right. The other thing that can happen with these same two reagents looks like this. One of these hydrogens, and this is similar to what we saw in the exam, same thing. We've got a strong base, strongly nucleophilic, but now instead of attacking this carbon and substituting for the bromine, another thing that can happen is that oxygen can grab a hydrogen on the carbon next to that carbon with the bromine. Those electrons go down to form a double bond, and the bromine gets kicked off that way. So the product from all those arrows, you'll notice this ethoxide is not attached to this ring. It simply pulls that hydrogen off, leaving this alkene. And so the byproducts are the bromide, and which also would have sodium, by the way, and then the ethanol. This reaction is kind of like the reverse of the addition reactions that we just did in the last chapter, and this is called elimination. In this case, it's called E2. There's an SN1 and an SN2, E1, E2. We'll get into that in a little bit. So neither one of those reactions are terribly complicated. They're single step. We can see what happens there. The tricky part is that both of these reactions happen with both of these conditions, with these same conditions. And there's a whole broad category of molecules that will do that. And so our task will be, in these types of situations, to figure out which is more likely. Are we going to get a substitution reaction, or are we going to get an elimination reaction? That's going to be our main point of this chapter. And then beyond that, are we going to get one or the other type of each reaction, because there are two types of each reaction. So that's the overall story of this chapter. It's going to take a while to get to that point where we can decide that well, but we're going to start looking at some of the different factors and figuring out how to make those decisions. All right. Yeah.
Okay, so I'm trying to figure out like the differences between those two. So the alcohol that isn't the alcohol anymore, the substitution reaction, where you said it's a strong base.
Right.
So the molecule under the elimination reaction, what is that?
Same thing. It's the same thing. I just didn't draw the sodium.
Oh.
Yeah.
So with those two molecules, both of these things are happening. The
right.
Substitutions happening and the elimination.
Right.
Okay. Oh. So the end is. Okay.
Yeah.
So we
sorry.
need to figure out which one is more likely.
Right. And so the way I've drawn it, actually, neither is more likely in this case. Well, maybe we'll get to that. But there are some situations. We'll have to start looking at some other situations where you might get one, you might get the other. Depends on things like temperature, solvent. There are various factors. So we'll get into that. All right, let's look at one mechanism at a time. So we'll start with the substitution. And then I'm going to introduce some terms with this as well. So we'll look at the two different types of substitution, the one we just saw, and then a related one. We're also going to get a little bit more specific about how we describe exactly what's happening here. We're going to start with what we call the SN2 reaction. Now, SN2 stands for bimolecular nucleophilic substitution. It's not really important that you know that, but it's the reaction that we saw up there. The 2 stands for bimolecular, which means 2 molecules come in at the same time and just substitute each other. There's nothing else going on. The rate depends on both molecules. Nucleophilic, because a nucleophile is involved, and then, of course, substitution. So let's look at what that looks like in 3 dimensions. So I'm going to draw a bromomethane here, but I'm going to draw it all out like we did before, where we're looking at all of the stereochemistry. Even though this isn't chiral or anything, just the 3D arrangement of this molecule. When a nucleophile approaches this molecule, and so that OH is going to be our nucleophile. This part, the carbon stuff, we're going to refer to as the substrate, so the thing that's being acted on. And then this part that gets substituted, we're going to refer to as the leaving group. All right, so we'll be referring to the nucleophile, the substrate, and the leaving group. So the nucleophile approaches the substrate directly opposite the leaving group. So if the leaving group is pointing out this way, the nucleophile has to come in behind like that. The reason for that is a couple of things. Oh, sorry. Oh.
Sorry.
Sorry. We started about, what, 10 minutes ago? So anyway, we're talking about substitution and elimination reactions. So in substitution, we have these three parts. The nucleophile comes in behind the leaving group and to attack the substrate. One reason for that is bonds, orbitals. So the anti-bonding orbital, if you've talked about that in general chemistry, is oriented behind, and that's where something has to come in order to get the reaction to happen. The other thing is you can just think about the how stuff is arranged. There's no room for it really to come in another spot, so it comes in directly behind there. So coming in directly behind there means that it's going to form this this transition state, which does not actually exist. Let's be clear. This is just, we're just going to draw what like the in-between would look like here. So if we imagine this coming in, but just as this has come in, but this hasn't quite left yet, it might look something like this. This is called the transition state. If we imagine a reaction coordinate diagram, this just has one hump, and this is at the top of the hump. So this is not an intermediate that you can isolate. This is just showing what it looks like when it's halfway through. The reason that's important is we can see how the geometry is changing. As that OH comes in on one side, it pushes those hydrogens away from it as the bromine leaves to give those hydrogens a little bit more space. So the final substitution product here is going to be the OH over here and it's pushed those hydrogens all the way back to make a new tetrahedron. So look at how those hydrogens have flipped from there to there. Kind of like an umbrella in the wind, just pops out the other direction. That's important because of the stereochemistry. So this is not a chiral substrate. But if that were a stereocenter, then that nucleophile coming in from behind would change the stereochemistry. It would actually flip it from R to S or S to R by doing that geometry. So that inversion is why we look at this mechanism in this way, in this SN2 reaction. So the things come together, and then they form those products. I'm not sure that the book really gets into that just yet, so we'll hold off on that for a second. And then we'll look at the companion to this, which is the SN1 reaction. The SN1 reaction actually does the same basic thing.
So
that one's SN2, yep. The SN1 reaction is going to accomplish the same thing. So we start with a substrate with a leaving group and a nucleophile, and then we end up with the nucleophile attached and the leaving group was left. Oh yeah, which we didn't draw over here. So we end up with the same thing, but it happens in a different way. It happens in a different mechanism, different steps. Right. So an SN1 reaction generally happens with a larger substrate that is more sterically hindered, which means it has more stuff around it. Something like this. So instead of a primary carbon or a methyl carbon like we have over here, we have a tertiary carbon, a carbon with 3 other carbons attached. We talked about those when we looked at carbocation stability. And so in this SN1 reaction, a carbocation is actually formed first. So rather than the nucleophile coming in at the same time that the leaving group is leaving, which I should have drawn that arrow also, rather than the leaving group coming on at the same time the leaving group is leaving, the leaving group leaves first. And then the nucleophile comes in later. So the nucleophile or the leaving group leaves, and you're left with not a transition state, but an intermediate carbocation. That means you can isolate that, you can see that. And then instead of that bromine attaching back, although it does a little bit, you have a nucleophile around that can attach. And that nucleophile is often not charged. It's often neutral. Something like water. So that water attaches itself, and it can go from either side, because now this is planar. This is symmetric. So it can go from either side. And then something deprotonates that final hydrogen, however you want to describe it. So more water would come in, take this hydrogen off, and you end up with basically the same product as we did in the SN2. You have now put the nucleophile on the substrate, and the leaving group, the thing that was attached, is floating around. All right. So far, all right, maybe? See how these two mechanisms kind of work and how they're different?
Wait, what's under the OH in the third?
This? There's a hydrogen there because this H2O attached. So both of those hydrogens are still attached there.
Then you added more water to that?
Yeah, or something else in solution that could deprotonate that. They could take that hydrogen off.
Why is, am I seeing things? Why is there CO? No, that's the
That's
air.
what I just said, yeah.
Where's the living? Oh, right here?
Arrow from the bond to the,
Let me redraw that.
I was like, I don't get it yet, but like, I don't think I don't get it that much.
Okay, wait, now I have a question.
Yeah.
So, the H2O attracted that hydrogen, so now you have H3OYs in the leftovers.
It is. It should be.
So then two middle stages are there are no transitions?
That's right. These are intermediates. So these are things that you can isolate, that you can see that exist. Only for a short period of time, but they do exist. All right. So the question, our first question then, before we get to the other half, which is the elimination reactions, the first question is, how do we determine whether two molecules will undergo SN1 or SN2 substitution? To do that, we have to look at the things that are involved in the reaction, the different parts that are involved. So we've got the substrate, that's the carbon part. We've got the leaving group, that's the thing that leaves, usually halogen or something like that in our case. Then we've got the nucleophile, the thing that comes in to attack. And finally, the thing we haven't talked about, the solvent. So what kind of solvent is this reaction being done in? So we're going to look at the effect of those four parts in order of importance, and then use them to judge how a reaction might proceed. Oh, I should say this. All right, so we'll start with the substrate. That's going to be our most important thing to look at first. What? There will be. This is just like sections. So yeah. Structure of the substrate. We're going to talk about how some, the reason this is important is some substrates can only do SN1, and some substrates can only do SN2, and then some can kind of do both. So we want to first look at the extremes, and then we'll have to use some other things to figure out that part in the middle. All right, so the first thing we're going to think about is the stabilities of carbocations. So one major difference in those two mechanisms, if we go back up and check, is that in this one, in SN1, we form a carbocation intermediate. Just as we did with the alkene addition reactions. So what do we know about carbocation intermediates? When are they more stable? Yeah, when they're heavily substituted. So that means that things like I'm just going to say Lg for leaving group. So something like that, a carbon that has 3 other carbons around it and a leaving group, is going to make a much more stable carbocation after that leaving group leaves. So when that leaving group leaves, this becomes a carbocation with 3 carbons attached. Do you remember what we called that? Yeah, tertiary. The symbol for that is a 3 with a little degree sign. Yeah, leaving group. Lg for leaving group.
I was like, is that some new?
Yeah, we're just going to throw in some new elements just for fun.
And now I missed it when I did, but leaving group, is that like a certain specific?
We'll talk about what makes a good leaving group when we get to that part, but yeah, it's something that can leave. For now, it's just the thing that disconnects. Yeah, in the substitution. Yeah, could have just been X. Would you like X? Is that better?
No.
Okay, Lg's good.
I wasn't sure.
Okay. All right. So then the other extreme of this is if we had something that didn't even have any other carbons on it, or just had one other carbon on it. Say that's a CH2 with one other carbon. If this tries to disconnect, as we know from the alkene chemistry, that doesn't even really happen. That primary carbocation is highly unstable and is really unlikely to even form. So that tells us that SN1 reactions are only likely for tertiary or sometimes secondary substrates. And not those primary substrates. Now there are some exceptions here when there's some resonance stabilization and some other stuff. We won't really get into that here. But for our purposes, that gives us a huge rule to follow already. Because if we see that tertiary substrate we can say, this is likely to go by SN1. If we see a primary substrate, we can say, oh, this is likely to be SN2 before we even start getting into all these other rules. So it's really only the part in the middle, those secondary substrates, where it's going to be a little bit back and forth. All right. The second part of that is if a more stable carbocation is good for a SN1 reaction, what kind of substrate do you think is good for an SN2 reaction? To answer that question, we have to think about what's happening here. The main distinguishing feature of the SN2 reaction is that this nucleophile is coming in at the same time before the leaving group has left. So that means that the crowdedness of the substrates is going to have a major effect. The name for that crowdedness is steric hindrance. How crowded is the substrate? We use that, I think we used that word steric hindrance when we talked about cyclohexanes. That big stuff in axial positions was sterically hindered, so that wouldn't occur, right? So it's the same idea, that a big bulky substrate with a big bulky nucleophile is going to be really hard to do an SN2 reaction. And so you end up actually with the same effect of that rule as the previous thing we just talked about. A tertiary substrate, if we get our models here, one, here. So here's our primary substrate. Let's say this is our nucleophile. And our primary substrate, and it has to come in behind there to react. And if this is just some hydrogens, not a big deal there, plenty of room. If we switch this out, I don't know what this is, but I'm just going to steal it. Yeah, so I just took some random parts here. But let's say we've got this molecule, that's still our leaving group on top there. But you can see this leaving group is going to have a much tougher time getting in there. Get stuck. Whatever. But anyway, you get the idea. So that backside attack of it coming in this way is going to be harder for it to do, harder for it to get there, which means that SN2 rate is going to be much slower. So when we talk about things being favored or less favored, we're really talking about how fast that's going to happen. Which thing is going to happen before the other thing. In this case, an SN1 reaction, where this comes off first, and then this can come into the top, might be much more likely. But it might actually happen faster than the SN2 reaction, where this has to come in through all this junk. So the next rule, another big star, highly crowded substrates especially tertiary substrates, which are already crowded just by the nature of there being three different things there. We'll say that they are bad for SN2. And when we say are bad, what we mean is they make it slower. So they give it time for another mechanism to come in instead, or to happen instead.
Okay, so SN2,
Yeah.
leaving group leaves after
No, yes.
SN2.
Well, it happens at the same time. SN2, it happens at the same time.
But SN1, leaving group leaves first and then.
Right, right. Yep. So that's the important distinction.
Is that why before you said you were against the that that's not small substrate?
Right.
That's not something.
Smaller substrates, or at least more available substrates. So you can still do SN2 reactions on a big molecule like this, but you're not going to do it right in the middle. You're going to do it out on the end here. So let's say we wanted to do a substitution on this carbon out on the end. That could still totally do SN2 because that's a primary carbon, and the thing could come in without getting into all this other junk. But this carbon right in the middle here, that becomes more difficult and slower. Yeah. So overall, that gives us a really nice shorthand here that is actually summarized in your book on table 7.5, or page 216, if you have that. But basically what we just said there, that primary substrates can't do SN1, so they'll only ever do SN2, and tertiary substrates generally only do SN1.
Hold on. One more.
But I'll write it down.
The SN2, SN1.
So we're going to say substrate in this column and the likely substitution mechanism. If we have what's called a methyl substrate, which is just a carbon with 3 hydrogens, that has to be SN2 because that carbocation is completely unstable. If we have a primary substrate, that also has to be SN2. If we have a secondary substrate, that could either be either, or that could be either, so we'll put a question mark, but actually this is usually SN2 also. And if we have a tertiary substrate, that's going to be SN1.
No matter what.
That's always a little too extreme, but pretty much.
For our class.
For substitution, yes. Where it gets a little tricky is when we also bring in the elimination reactions, which compete also. So a tertiary substrate can do substitution or elimination, but when it does substitution, it's always going to go SN1. All right. So now we've talked about the substrate structure. Let's talk about what makes a good leaving group and how that affects it.
It's like number 2.
Yeah, this will be our second factor. So our leaving group is the thing that leaves. And what do you think determines whether it's a good leaving group or a bad leaving group? What's going to speed up or slow down a reaction based on the leaving group?
What the leading group is.
Yeah, right. So like what? Polarity is going to be part of it, yeah. So let's look at a couple possibilities here. Let's look at an iodine with attached to a bunch of carbons versus an OH attached to a bunch of carbons. And let's imagine both of those things leaving. Since we're forming the same, we've got the same basic substrate, we're forming the same kind of carbocation, it depends on the stability of that anion. So what do you think? What do you think is going to be more stable, an iodine ion or a hydroxide ion? Why? Okay, just a guess. Other ideas? Other guesses? Yeah. Maybe. In this case, what we're really looking at is how can we stabilize that negative charge? So that both of those are charged. What's going to be a more stable negatively charged thing? Any idea how we might determine that? We can look at the periodic table. In this case, it's going to be determined primarily by size. That iodine is much larger than oxygen, right? Because it's however many rows lower, so it's much bigger. So that means that that negative charge is spread over a larger area. And it also has a lot more protons to help pull that negative charge in, or to help offset that negative charge. Hydroxide, the negative formal charge is on the oxygen, and that's much smaller. So it's a much more condensed, dense negative charge. And that makes the iodine much more stable with that negative charge. Yeah.
Is that how we would determine it a lot of the time?
A lot of the time, but not all the time, unfortunately. So we're going to look at some different things. Yeah. The iodine is more stable. In general, a shorthand for this is which one is going to be a weaker base. The weaker the base, in general, the better the leaving group, because it's more stable on its own. If it's a weak base, that means it's okay to just hang around as a negative charge. It doesn't need to grab a hydrogen. The other nice thing about thinking of it as a weaker base is it allows us to think of the acid and then use that to judge. So for instance, the conjugate acid of IA is what? If it gets a hydrogen, what is it? HI. And the conjugate acid of OH is what? Or conjugate, yeah. If OH gets a hydrogen, what do we have? H2O. So that means that this is going to be a much stronger base because it wants to grab that hydrogen to make it a nice stable water molecule. Whereas when this grabs a hydrogen, it's just a strong acid, HI. So this one is happy to sit around on its own as a negative charge. This is going to really want to grab a hydrogen. And that makes this one a stronger base.
How do you know it's based on?
The negative charge. Negative charge. Right. Oh, so which one? How do you know it's more basic?
Yeah.
The way I think of it, well, one way is the first way that I said about spreading the charge out, so it's not as like condensed, not as dense. The other way is to think about what the acid would be when it gets that hydrogen. If that's a strong acid, that means the base is a little more stable. If that's a weak acid, that means the base is a little stronger.
How do you know that it's, sorry, this is like general chemistry. How do you know that it's a strong acid? Like, how do you know it? Like, I know that HI is a strong acid, but how do I know that?
I don't know. How do you know that? Yeah, you just remember it. So there's like a handful of strong acids, and a lot of it has to do with polarity and things like that. But there's also just that list of strong acids that you probably remembered at some point, and that was on there. Maybe, I don't know.
Is that from this semester?
No, from general chemistry. So yeah, if you're, there is a nice review of that stuff in this book, chapter 2, which we didn't really go through because it's really general chemistry stuff, but that might be helpful for this chapter to go back and look through that, some of that pH, pKa stuff, if you haven't thought about that in a while. So the other answer to your question is you look up the acid on a pKa table and you figure out what's the stronger acid and what's the weaker acid on that.
But we're not going to be given a pKa table.
Depends, but yeah, right. So you'll just get used to it as we work through this, I think. So the better leaving groups are generally these weaker bases that we see. And the book has a nice chart that I'll just go through here. And just a short one. So really good leaving groups are things like iodide and then the other halogens. All of these are good leaving groups. with the exception of fluorine. It's more stable on its own. So what that means for us in terms of a substitution reaction is it's going to increase the rate of the substitution because it's easy to leave on its own. It also, in some cases, can favor an SN1 reaction because it can just leave easily without the nucleophile having to come in. But we're getting a little ahead of ourselves there. Other good leaving groups are things that are already neutral, things like water. Right? If water is attached to a molecule, it's going to have a positive charge, which means it's going to want to leave and just be neutral on its own. Any neutral stable molecule is a good leaving group. And then much weaker than that are leaving groups where the negative charge is not well stabilized. So things like OH minus, CH3O minus, NH2 minus, that kind of stuff. All right, so that's an example of the leaving group. And then when we get into all this together later, we'll come back and say, okay, remember how we decided what was a good leaving group and what wasn't. And we'll come back and look at this. Okay, so the next thing to discuss is the nucleophile. That's 3. The structure of the nucleophile and what makes a good nucleophile. Now, nucleophilicity, as it's called, like what's a better nucleophile than something else, is a little bit tricky because it depends on a couple of things. It depends on something called polarizability, which we're not really going to get into. But basically, if you think about what a nucleophile does, it has to take its electrons and push them out and connect them to a carbon. That's what the nucleophile does, right? It takes its electrons, it attaches them to a carbon. So it has to be, it has to have electrons, it has to be nucleophilic, it has to have maybe a negative charge or something, or negative polarity, but it can't be so strongly negative that it wants to hold its electrons to itself. It has to be able to give those electrons to a carbon, right? Push those out onto a carbon. So that makes for some tricky distinctions about nucleophiles, but we can simplify that by putting them into a couple of good groups. And the book does this, and I think this works well. So we're first just going to look at what we would call the really good or strong nucleophiles. Some of them are a lot like the leaving groups. So iodine actually is a good leaving group and a good nucleophile. Sulfur-based nucleophiles are usually really strong. Because, again, sulfur is larger than oxygen, so its electron cloud is a little bit, that negative charge is a little bit more diffuse, a little bit more able to go grab things. CH3S. CH3S. And then oxygen nucleophiles can be good too, but I'm going to put them in parentheses for one particular reason. So things like hydroxide, methoxide, and just any general, R just means general carbon stuff with an oxygen negative. Those are strong nucleophiles, but they're also really strong bases. So the other stuff we've drawn are good nucleophiles and weak bases. These are good nucleophiles and strong bases. And that is going to maybe give us some trouble later when we talk about elimination. So let's remember a little bit in the back of our heads that, yes, these are good nucleophiles, they're strong nucleophiles, but they're also strong bases. Okay. there's a whole list in your book, good, moderate, poor, whatever. You can look at those. I'm more interested in just showing you what makes a good nucleophile versus a bad nucleophile. So if you want all those details, you can look. Let's look at some of those poor nucleophiles. So poor nucleophiles are going to be things that maybe are still nucleophiles and can attack things as nucleophiles, but just aren't going to be that fast about it. So that's things like water, alcohols in general, whether methanol or an ROH, and then things like carboxylic acids. So these things are still nucleophiles. They have oxygen, which means they have lone pairs that can go out and attack stuff. But they're just not going to be that good about it. They're going to be slow. And the reason for that is that they're not that nucleophilic. When they attach to something, they're going to have a positive charge, whereas these negatively charged things are going to attach really strongly. So a stronger nucleophile will generally have a negative charge. A weaker nucleophile will usually be neutral. So how is that important? Well, we'll tell you. Stronger nucleophiles favor SN2 over SN1. Go all the way back up to our mechanisms. This first step in the SN1 reaction where the leaving group leaves, this is the slowest step. That takes the most time. So if you have a really strong nucleophile, that nucleophile might be able to get in there before that leaving group has a chance to detach and force the SN2 reaction. Now that doesn't violate our rules from this table. But when you have that question mark, that's when you can go look at the next thing. And so you can look at that nucleophile and say, oh, that's a really strong nucleophile. So that's probably going to go SN2 instead of SN1. Okay, and then the very last factor is the solvent, the stuff you're actually doing the reaction in. First thing about the solvent is that you usually need a polar solvent to do these reactions at all. Because these things that you're reacting are usually pretty polar. The nucleophiles are maybe negatively charged. The substrates are often polar. So you usually need somewhat of a polar solvent to do this in the first place. So there are two categories of polar solvents that we're going to consider. And we're going to call them protic and aprotic. What do you think that means? Any ideas? Protic solvents are hydrogen bond donors. So molecules that, or solvents that can interact with a hydrogen bond. So usually things that have OH or NH. And aprotic are polar solvents that don't have those. So, for example, the common protic solvents are things like alcohols. So water, methanol, ethanol, things like that. Maybe ammonia, any alcohol, ammonia. Those are protic solvents because they have that OH or NH that can hydrogen bond. Aprotic solvents are polar solvents that don't have that. And these we're often not as familiar with. So I'm going to draw the structures and say the names. So things like acetone, That's a polar solvent. It's got that CO bond, but it doesn't have that OH or NH in it. Some other common ones, which we've used, dichloromethane or methylene chloride. Diethyl ether. And this is commonly used, although I don't think we've used it yet. Dimethyl sulfoxide, DMSO. That one's often used in medicine as well. It has the property of being able to take things through the skin. So something dissolved in dimethyl sulfoxide, you can put it on your skin and get it into you. You'll notice all those structures are polar, but don't have those OH or NH parts to them. The protic solvents favor SN1, and the aprotic solvents favor SN2. Any idea why that might be? Go back and look at those mechanisms. Look at the differences in those mechanisms. And try to see how those solvent groups might favor one versus the other. Yeah, dimethyl sulfoxide.
Wow. And that's one you add water. Right?
We did, that one, yeah.
Add a protic, maybe?
Right. So think about how it might speed up or slow down one mechanism or the other, and why. Ideas?
Well, aren't you? In SN1, aren't you slowly diluting everything? Like more? The process can go
Yeah.
longer.
Yeah, and it's forming that carbocation,
Yeah.
right?
Yeah, and then SN2 all at once. And that has to do with boosting, but.
Yeah.
But-
You're sort of getting there. The main thing with SN1 is that we're looking at these carbocations. So whenever you can better stabilize that carbocation, you're going to favor that SN1 reaction. And that's something that these protic solvents do. Something like water. So let's say we have a carbocation like this. A water molecule is really highly polar. So that partial negative charge on the oxygen can surround this carbocation and make it very stable. At the same time, we can take a nucleophile and stabilize it. So if we have a really good nucleophile like iodide, and we put that in a protic solvent like water, we're going to have the same effect, but that actually hurts our reaction. Because now the iodine is happily surrounded by water molecules and doesn't really want to go attack anything. So the protic solvents stabilize carbocations and nucleophiles. And so that speeds up the SN1 process and slows down the SN2 process and ends up favoring SN1. What?
So I don't understand why these do a better job of stabilizing. Do the aprotic ones not stabilize at all? They just do it more slowly, or what?
They don't as much. So the reason that these OH and NH are special is that has a much greater difference in electronegativity, and so a much more polar solvent. That's why even though ether, like diethyl ether or dichloromethane, those are somewhat polar, but they will still separate from water because water is just that much more polar, like in the separatory funnel. So yes, these can interact a little bit with those carbocations, but not nearly to the extent that these can. So it's going to be a much, much stronger effect.
So are all the ones that you wrote here with Protic, are they all tertiary?
Well, these are the solvents. So this would be the liquid that you do the reaction in. Tertiary applies to the substrate, the thing that's being reacted on. The thing that has the leaving group that's being reacted on. Though sometimes what happens is, I'll show you an example of this, sometimes the solvent can also be the nucleophile. So in an SN1 reaction, like we saw, which you pointed out, that in our example way up here, in our SN1 reaction, we actually react with water as the nucleophile. So in when we want to do an SN1 reaction, we might often just put something in with water to do that substitution. So in that case, the water is both the nucleophile and the solvent. That's usually not going to work with an SN2 reaction because we want a stronger nucleophile. We want something that's charged. And so we're going to use something like sodium hydroxide in one of those aprotic solvents instead. All right, so let's do some examples where we look at which mechanism we're going to have and try to figure that out.
So BR is the tertiary?
Yeah, yeah.
How do you know it's tertiary?
Because this carbon site, which is where the substitution is going to take place, has 3 other carbons attached to it. Yeah. All right.
So
Yeah.
How do you know it has that? Because it'll be given to us just like this?
Right, because you
Like
look
when
at it.
it says react BR with H2O.
That's not that. It's not the bromine that's reacting. The bromine is the leaving group that is attached to this whole molecule.
Okay.
So you would say, what is going to happen to this whole molecule when it does whatever?
Okay.
Yeah. Okay, so I'm going to put down a couple reactions here, and you're going to decide what the product is likely to be. And what the mechanism is that this goes by. right, so we've got 3 here. Should we do one together? Okay, which one do you want to do? Well, we'll do one together, and then you can work on the others with the people at your table, and then we'll talk about it.
The bottom one.
The bottom one. All right. So here's how you think through this. Here's how you think through these. So we're going to look at this, and first we're going to see that this is likely a chapter. We'll call them a chapter 7 type reaction. So substitution or elimination. We haven't gotten to elimination yet, but so we'll say substitution. And we're going to see a few things here. We see a substrate, the main part of the molecule. We see a leaving group, which is Br. And we see a nucleophile, which is, and we see a solvent that is water. All right, so we have to think about what is going to substitute and why. So this is a substitution reaction. What substitution happens? What substitutes for what? So the bromine's that leaving group, so we're gonna get rid of that, and what's gonna end up in its place? OH, right. So the nucleophile minus a hydrogen because it's neutral. So if we just stuck H2O onto there, that O would have a positive formal charge. So we have to get rid of a hydrogen to make it neutral. So the product should look something like this. It's just more practice, right? And then bromide would be a byproduct, but we'll focus just on the main part of it here. What? Okay, how do you know that that's what happens? Let's look at that. So to figure, what? So to figure out what's going to happen, we need to follow a mechanism. But to know the mechanism, we have to decide if this is likely to be SN1 or SN2. So what kind of factors can we use to decide if this is going to be SN1 or SN2? What would we look at first? So first we look at the substrate. And what is the substrate here? What type of a substrate is it? Yeah, it's a tertiary substrate. So the carbon attached to the leaving group has 3 other carbons attached to it. And that tells us that it's a tertiary substrate. And now, without even going into anything else, we can say that this is likely to go by an SN1 type mechanism. Now, when we get into elimination, it won't be that easy because tertiary substrates can also do elimination. But for now, we know that that's definitely not going to do SN2. Okay, so now that we've got that, we can start drawing that mechanism and start showing what's going to happen. What's the first thing that happens in the SN1 reaction? The leaving group leaves, forming the carbocation. So the bromine comes off. And we're left with a carbocation.
That, I was looking at it right, that's 6 cyclohexane, right?
Yeah, yep. Sort of. Yeah. Actually, what's going to happen is there's no OH around because there's no base, so water will attach there first, and then we'll have to get rid of one of those hydrogens. The bromine just floats away on its own, so we won't even draw it here. So the product from that is this. That water is attached. Oxygen with 3 bonds is always going to have a positive formal charge. So we need something to get rid of that last hydrogen. The thing that's going to do that is more water hanging around in solution. Takes off that hydrogen Well, and then we're left with that product. No. Generally, we'll just be concerned with the major organic molecule, and the other stuff we'll just assume is gone away wherever. Yeah. And you may not always need to draw the mechanism. I mean, if I ask you to draw the mechanism on the test, you draw the mechanism. But if I don't, the mechanism can be really helpful as a way to figure out what the product is going to be, or you may not need it because you may have done enough practice and it's just clear to you. But we can use mechanisms. The reason we think about the mechanisms is we can use them to help us predict what's going to happen when we encounter new molecules that we may not recognize. All right, so that's that one. So let's see if you can do a similar discussion among yourselves with those first two. Determine the mechanism and determine what the product would be based on that.
We still,
Yeah.
like what we're adding, like the CH3OH, that's, we look at product of product.
Sure, but remember that's the last thing to look at. So first you're looking at substrate and then the other stuff. Yeah. In this case, or at least just say what it would be.
Like the end result?
Yeah, and what the mechanism would be if you were to draw it, which one it would go. SN1 or SN2. Yeah.
I don't have any nucleophile.
You don't.
No, I mean, just taking this at face value, like looking at it really.
Okay.
I have 2 solvents and no nucleophiles.
Okay.
So,
Let's talk about it all together because I bet others have so much.
yeah, okay. Okay.
Can you ask your question louder so everyone can hear? We're going to look at that first one. I thought that was a good intro. So the question was, it looks like there's solvents. What's the nucleophile going to be in this first one? Anybody come up with a response to that? An idea? That would be the leaving group. So let's look at this. What is this first thing? This NaOCH3. Yeah, so that's going to be a sodium ion because we know sodium only forms ions with other stuff. And then this, which is known as methoxide. So that's going to be the conjugate base of methanol. So this is very similar to something like hydroxide, but instead of OH, it's OCH3 with a negative charge on the O. So if we go back up to the nucleophile list here, right, that's going to be one of those strong base nucleophiles. So that's your nucleophile right there. That's the thing that's going to be a strong nucleophile, that methoxide.
So altogether, what? I'm sorry. This is so. What's the strong nucleophile? The Na.
No, remember a nucleophile. Well, yeah. So right. So a nucleophile needs to be generally either neutral or negatively charged, because nucleophile means it wants a nucleus. So it wants something that's positive. So it's going to be something negative. The nucleophile part is the OCH3, the methoxide. But you can't just get a jar of something that's negatively charged. So it's always going to come with something positively charged to counter it. So when you put that in solution, it's going to break apart in solution just like other ions and form sodium ions and methoxide ions. And the methoxide ions are going to be the thing that attack the substrate in a substitution reaction. So you can ignore those metal counter ions when you see things like sodium or potassium or lithium in a reaction like this. Those aren't going to participate. Right. That's what.
But then that's where my question is. You said we'll run into problems with that though, but
Why?
not yet, right? You said
Oh, not in this case. So I picked out an example where you would, but you will see that later. That because those can promote elimination sometimes. So does that help with the first one? Yeah. Okay. Good. All right, so this first one then, what's your pick for the mechanism? Yeah, this is SN2. How do you know?
I couldn't figure out the structure first, so I stuck that. And then I was the leaving group, and I saw that it was the BR. And then I went to the Nucleophile, which just starts the CH3L.
Mm-hmm.
And then I went to the Protic and Aprotic, and I saw there's ether, so and then
Okay.
basically 3 out of 4 got me gas.
Okay, good. Anybody find something else? Yeah, that this is a primary substrate, meaning that this carbon it's attached to is only attached to one other carbon. And so that means it actually can't be SN2. So it has to be SN1 in that, or I'm sorry, it can't be SN1. It has to be SN2 in that case. So the mechanism would look like this. The O would attack the carbon, the bromine would leave, and you end up with something like that. And that should be the product. Okay. You can, but it's usually not, it doesn't give you any more information. So I'm not sure it's necessary. That was just to kind of show what it looks like. It doesn't really help you get the product though. Yeah, so the Na is paired off with the Br that has left now. And those would just be in solution. All right. One other thing, since we're talking about byproducts, so we did the extraction labs, you know, where you do the separatory funnel thing. When you do reactions, you usually do an extraction after the reaction with just plain water or maybe a sodium chloride solution or something. And it's to get rid of all this extra stuff. So the reason we often don't care so much about that when we write them is because at the end of a reaction that we actually do in the lab, we would get rid of all that through an extraction. So you would extract, shake it up. The neutral product would stay in the organic layer, and the charged salts would go into the aqueous layer. You drain that off, and then they're gone. So all that extra charged stuff will come out in the wash, as it were, in the extraction afterwards.
So why is I'll ask you.
Okay. Let's look at this last one then. So what do you see going on here? SN1, why? Yeah, so once again, we see that tertiary substrate. We know it's not going to be SN2. So I didn't put any tricky secondary substrates in here yet. We'll get to that. So if this is an SN1 reaction, what's the product of that reaction? Didn't get to that part? Well, it's actually going to be the same as what we see down here. Not OH, because this is not an ionic compound. So that does not split up like that. What's going to happen here, this is methanol. This is a weak nucleophile. that's going to attack in its place, and then that hydrogen's going to come off just like it did with water. So that whole molecule attaches, and then just the water gets just the hydrogen gets taken off, and so we end up with OCH3 attached there.
So what's floating around this?
So floating around would be I minus and H plus. But that H would probably be connected to another methanol molecule. All right. Okay, with our last 5 minutes, let's look at what happens when it's more in the middle. So we're going to take this chiral substrate, 2-chlorobutane, but this is a chiral 2-chlorobutane. In fact, this is R2-chlorobutane. And we're going to do two different reactions with that, with similar reagents, figure out which one is which mechanism and why that's important. So first, we're going to react that with sodium methoxide. It's going to be very active in, we'll say in DMSO. And then we're going to react it with methanol. So what's the difference in those two conditions? First of all, how would you determine the mechanism in these cases? It's secondary, so you can't just rely on the substrate to determine which mechanism you're going to get, because you can get either one, depending on your conditions. So which conditions seem to favor SN1 here?
The bottom.
Yeah, the bottom, the second one. Yeah. Right, why? Right, that's going to be a protic solvent. And also, this first one has this aprotic solvent and a very strong nucleophile. So that's going to likely be SN2. All right, so we can draw the products of these based on the mechanism. Because we're running out of time, I'm just going to do it here. And we'll see the difference. So the product from the SN2 reaction is only one product. S2-chlorobutane. Product from the SN1 reaction is a 50-50 mixture of the two enantiomers, which we call a racemic mixture. (50% one enantiomer, 50% of the other). In other words, it's not chiral, or it's not what we call optically active anymore, meaning that it's lost its stereochemistry and it's now a 50-50 mix of the two enantiomers. But notice the connectivity is the same. So in both cases, we're substituting an OCH3 for a Cl. But when we choose the SN1 reagents, we end up with a racemic mixture, a mixture of stereoisomers. When we choose the SN2 reaction, we end up with one pure stereoisomer that is the opposite of what we started with.
Wait, I have a question.
Yeah.
When we have this situation, we're picking which one we would go with, like the end result, or is this like a situation when you're doing it both ways?
I would say, I mean, in this case, I was just asking if you could figure out the mechanism for each one and what the products would be because of that. In general, in an experimental situation, you probably wouldn't ever want this bottom one. So this would be something you'd want to avoid. If you wanted to make this, you'd want to do it this way. The name for this idea that the stereochemistry is flipped is inversion of configuration. And it goes all the way back to those mechanisms we looked at. In the SN2 reaction, the nucleophile comes in the back and that geometry is locked. It has to go in that separate way, and that umbrella effect means you're flipping the stereochemistry. In the SN1 reaction, the leaving group leaves, and suddenly you don't have something, you have something that's achiral. The carbocation is flat. So that nucleophile can come in from one side or the other side, doesn't matter. So you end up getting a 50-50 mixture of the nucleophile on one side or the nucleophile on the other side. And when there's chirality there, that means you're going to get a mix of enantiomers. That's the difference in the two. If you are dealing with chiral substrates, and you usually want to control that stereochemistry, so you usually want to avoid those SN1 type reactions. All right, that's all the time we have. Should we do a quiz on this on Monday? Probably should, huh? All right, so we'll do a quiz on this on Monday. Oh, you're right, it's not. Methoxybutene. Methoxybutene. Butane, yeah. Methoxybutane. Thank you. You're right.